So my name is Sungjoon, and I'm assistant professor at Korean University. And today I'm going to talk about Tor as a natural motion generator. And this talk will be a little bit different from what two professors had talked about. So mainly, like Pomjun talked about like manipulation, task and motion planning, and Jaemin talked about reinforcement learning and locomotion designs, controller designs. And today, what I'm going to talk about is more towards a human-robot interaction and natural motion generation of a humanoid robot. So before going on, let me introduce what Bill Gates has predicted in 2008. So a robot in every home. So a leader of PC revolution predicts the next hot field will be robotics. So I pretty assume that all of you who are listening to the seminar should be interested on building a robot and let that robot to be useful inside our daily lives, right? And a robot in every home is basically what we need, but it has not come yet. So this article was written in 2008, and Microsoft basically built the Microsoft Robotics Studio after then, and they stopped their service at 2016. So what was the problem then? I mean, there are a lot of problems, a lot of hurdles on deploying a real robots in our daily lives, other than factories. And try to, one of the issue that I think is that the motion side, especially the motion that is being generated by the robots, are pretty too robotic. And I assume that, or I presume that, that if the robot motion were more natural and expressive, I think more people will be interested in robotics, and that's the field that I'm interested in. So instead of giving you like, catchy word, this is my introduction. So my passion lines are future robot twigs with human beings, where my personal goal of developing an intelligent companion robot. And this has been my phrase for like decades. So I was always interested in robots that coexist with human beings, especially not only about giving some, physical assistance like in smart factories and stuff, but also in human robot interaction and social robot science. And especially, I joined Disney in 2018, and I saw that there's a bunch of robots in Disneyland and Disney World. So for those who have not been to Disney World and Disneyland, unfortunately, if you're from the upper part, that is the Pandora Land in Disney World, Florida. The right side, that's the Captain Hondo on the Disneyland, the Galaxy Edge. On the bottom, that's the Belle and the Beauty and the Beast in the Disneyland Tokyo. And the robot is the robot that's inside these robots. So I was fortunate enough to see all of these robots, and not only the hardware is very impressive and very expressive and expensive, but also the engineers at Disney actually worked pretty hard on making these motions natural. So that was the thing that I worked with Ju-hyung when I was in Disney. And the main hurdle was actually the time the animators or the artists took to make this 5-minute or 10-minute video at the animation, the animatronic motions. Nowadays, you see a lot of YouTube videos from Boston Dynamics, and they hire professional choreographer to design these robots. And if you see some of the workshop done by Scott, then they put some effort on designing this dancing motions of Spot and Atlas, and that's very expressive. And I think they give a whole new horizon of the robotics, especially in the entertainment side, as well as like social robots and human robot interaction sides. So today's talk, I'm going to focus on how we can generate robotic motions, especially on the humanoids, from motion capture data or even from the scratch. So these are the contents, and I try to, because of the limited time, I only got like 25 minutes. I'm just going to give you a lot of a bunch of videos that I made, and if you have any questions, more details, please let me know. I'll be more than happy to explain all of the algorithms in detail. So first, I'm going to talk about optimization-based motion targeting and learning-based motion targeting. And then I'll move on to the conditioned motion betweening and the interactive robot bus, which is basically human-robot interactive agents. And let's start. So this is the first work that I did when I started my postdoc at Disney Research. As I said, the main bottleneck, one of the main bottleneck of deploying diverse motions and the Disneyland and Disney World is on the time that it being consumed for generating animatronic motions. And one of the natural or intuitive or straightforward idea is to leverage diverse motions out there, motion capture data or even YouTube, and try to use post-assessment algorithm to come up with skeletons of a human and then transfer it to robot. So that basically is called the motion targeting. So again, the process of generating robot motion from motion capture data is called motion targeting. And this is a problem that I'm gonna mainly doing what I mainly did and what I'm mainly doing even nowadays. So there are a bunch of problems out there, right? First problem is different skeleton from different motion capture data often have significantly different shapes and morphologies. So on the left side, these are the video from the CMU mocap data. On the middle, that's the in-house data we collected from digital research. And right side, that's animation data. And if you look inside the skeleton, all the skeletons are different. So even with the same human beings, based on what kind of mocap system that you're using, like Vicon, OptiTrack, or different stuff, the shape of the skeletons are different, and it often becomes a bottleneck on leveraging a diverse set of motion capture database. So if you see a lot of papers, they only use a single motion capture device or a single format of the motion capture data so that they could easily use or fine tune on that data set. So here you can see that the CMU mocap database, emotion mocap database, and Frank mocap database, these are the motion capture database that I am using actively right now. And you can see that the number of joints are different. And of course, the structure is of course different. So we have to have some idea of somehow using a common ground so that we could leverage all those different motion capture database. And of course, the core goal of motion targeting is to transfer the motion to the robot. So different humanoid robot often have significantly different shapes and morphologies. So here, OP Darwin from robotics, Coleman from IIT, Thormang, and the adolescent, you can see, all have different form factors. But they not only differ in sizes, but you can see inside, the biggest problem, I think, is that it has all different degree of freedom and range of motion. And if the form factor is small, then it's actually more prone to self-collision, making the range of motion more restrictive. So you have to consider those physical limitations as well as velocity and acceleration threshold limitation of the actuators. So this is called the common rigging that I presented, that I'm working right now in order to resolve the first issue. So you can see that we're leveraging a different motion capture database, CMU mocap, emotion mocap. And what you see on the Frank mocap is that is the post estimation result that we get from the YouTube videos. So you can see that even though all of these skeletons are different in terms of number of joints and hierarchies, we were managed to map all of different motion capture data into a one single rig, which we call the common rigging. And the third problem is some of the estimated motion may not be physically targetable. So what I mean by that is, especially when you're using a post estimation algorithm, and the algorithm that we're actually using is called the Frank mocap from Facebook AI or Meta AI. So this is the still image that I just brought up. This is a man standing still. However, the estimated pose is like this. You can see that it's a little bit inclined forward because of the lack of the depth information from RGB camera. So if you just use this pose directly to robot, you can see that the center of mass is actually outside the contact polygon. So it means it's more likely to fall off. So we have to come up with a method so they can at least maintain some stability. So we also brought up some post-processing method called the post-humanization, so that we can actually optimize the pose of the common rig so that the other parts of the body remain the same, but the center of mass should lie within the contact polygon. And after that, we transfer into a different type of robots. So this is like the whole pipeline that we are developing right now. And you'll see a bunch of results sooner. So this is an overview of the algorithm that I presented on 2019 IROS. And it's basically try to use an optimization-based method. So the thing that we optimize is the length of the human skeletal animation rig, so that it matches that of the robot. And after that, we get the desired target position per different joints, like shoulder, elbow, hand, wrist, pelvis, knee, and so forth. And then we solve inverse kinematics and we do post-processing. So all of these are kind of straightforward things that you can thought of. However, because this optimization is not differentiable, we use a black box optimization, and I kind of combined the coordinate descent algorithm with the Bayesian optimization to come up with this idea. So this idea was kind of crude, and it was a preliminary work, and we're developing this idea into a more complex scenarios. And actually, I'm doing collaboration with Naver Labs, and I have fortunate enough to work with Ambidex. So I'm going to show you some of the result that I made on the Ambidex. So here, this is a result that I presented on IROS. This is the dizziness work. So mocap data to different robots in simulation environments. And of course, we can also motion retarget from animation data to different robots. And ta-da, and this big, so all these motions. And of course, we can not only do inside the simulation, but these are two robots, Thormang and Poman are two robots that I was able to use in vision research. So I also mapped those motions to the robot as well. However, you can see that this large 2x. I mean, for those who are doing robotics, you'll probably be familiar with that. So I mean, I slow down the robot speed, and main reason is about two things. One is the stability, and second is the lack of the tracking performance of the actuator. So for multiple reasons, the robot, the P gain was really small, so we weren't able to fully track the speed, which was kind of sad for me. However, if you use Ambidex, which you're going to see, it kind of tracked the original speed of a human, which is really a joy for me whenever I watch. So here is a motion retargeting, the recent motion retargeting result. So you can see on the left side, the mocap data is from CMU mocap data. And even though the humans are moving around, it's not a good idea to transfer the whole body to the robot, especially the foot. If you were to mimic the human foot behavior, then things become extremely difficult because of all the stability constraints, especially on the humanoid. So what I did is I found some optimization method that could constrain the location of it and also the center of mass within the fit. But I'm gonna let other parts of the human to match the robot. So you can see that the ankles are moving, knees are moving, but the fit location is always stand still. So here we can see that the same mocap data being transferred to Atlas, Coleman, Thormang, and Darwin Mini. And then these are the results that I got from Naval Lab, all approved. So this is a driving car data, motion capture data from CMU mocap data. And one thing to note is that all of the pipelines are automated. Means that whenever you have any motion capture data available, not only from CMU mocap data, but also from YouTube, for example, then we have a whole pipeline of generating or transferring those motion, human motion, to the robot with all the collision handling and all the center of mass handling, all the smoothings and so forth. So this is a very exciting work. This is the second motion, shooting a gun. You can see that you have a little bit of jiggling on the waist side, but otherwise it's pretty fast. And if you see this robot in real, it's pretty big and really fast, and it's really, from my end, it was really fantastic moment to see this motion happening. And this is one of my favorite motion called the playing a violin. And you can see that the Ambidex is trying to do playing a violin. Okay, so these are the results that my team is working on right now. So second topic of my talk is about the learning-based motion targeting. So why we need learning-based motion targeting, even though we can basically do motion targeting using the optimization-based method? And the main reason for this the learning-based motion targeting is about speed. For example, even though the optimization method is like the fully automated, it may take about 30 minutes to generate like 20 seconds of motion. So it may be fast enough to generate a bunch of motion if you have like a clusters. However, if you think of like the movie of Real Steel, it may not be fast enough to do real-time interactive robots. So we want the robot to mimic human beings on the fly, like the online manner. And one way of doing it is to leverage the machine learning algorithm. So finding a mapping between pose and robot. And the naive approach you can think of is to directly find a mapping between human pose space, like the skeleton positions, to the robot joint angles. However, the approach that I did is called the shared latent space modeling. So the way we do that is among different domains of human, or animation, character, or different human and different robots, we want to build a shared latent space that could freely move around, meaning that we want to train a domain-specific encoder so that we can freely map each point or pose of a human to the shared latent space, and then decoder so that we can freely transfer the knowledge into different robots. And by doing that, we can not only do motion targeting from a human motion capture data to robot, but also we can reuse the motion that we generated on robot A to robot B. I mean, if you have played with robots, you probably know that whenever you generate a robotic motion from key point matching, it takes some time. And once the project is done, when the robot is changed, for example, you add more actuator on that, that motion is very likely to be just wasted. You cannot use that anymore. But if you are able to find this to share latent speed nicely, then you may be able to reuse that motion again to different robots with a little bit of slightly different actuators. So the way we do that is pretty, intuitive. So we have a different domains of mocap and robot A and robot B. The first we need is the data. So we need a paired data between motion capture data and robots. And the way we collect the data is, of course, using the optimization-based mission target that I presented before. And then using those paired data, we could find a shared latent space, meaning that we can find a same dimensional latent space so that all of the paired data should lie within a similar position inside the latent space, which is called the latent consensus loss. And then we basically have a reconstruction loss. And the reason why we need the reconstruction loss is to maintain the one-to-one mapping instead of like the mode collapsing stuff. If we want the latent space to be well structured, so it's called the latent prior loss. So all of these structures is exactly the same as what variational autoencoder does. So I use a variant of variational autoencoder called the Wasserstein autoencoder, which is empirically better in my case. So that's how we collect the data and how we train the model from the collected data from the optimization-based method. So this is to show you. So I constructed a two-dimensional latent space. Of course, we use a bigger dimension in the real application. However, we can see that on this two-dimensional space, similar space and the latent space result in the similar pose of robot, even though the number of joints are different per different robots, so Coman and Thorman. And let's see. So this is the result that I get presented on the RAL 2020. If the motion shows up. So you can see that the robot is successfully following the human behaviors from the motion capture data. However, this was not online. The main reason is that even though the human pose transferred to latent space and then decoded to this Thorman, it was fast enough for online matter. It took about like 20 or 30 milliseconds. The biggest problem is that the output of the neural network is very unlikely to satisfy our some feasible constraints. This is not only the problem of this latent space modeling, but it's also like a general problem of machine learning, so that the output it's really hard for output to guarantee to be in some feasible set. So the recent work that I did on RSS 2020 was to combine the non-parametric method with like a lookup table method with this latent space modeling so that we can combine the best of two worlds and to come up with a real-time method. So you can see that it's not fast enough, but however, it's a real-time, like an online manner. And that is that is my friend Matt, who's an assistant professor in Princeton University, and lower side is myself on that suit. It was a little bit small for me. Okay, so that was the stuff that we did on generating robotic motion from motion capture data. However, it's not always possible to have a motion capture device in your lab or in your industry because it's expensive. It takes some space, and of course, my lab doesn't have it yet. So we want to generate motion data from some conditioning without the necessity of leveraging all those motion capture devices. So it's called a conditioned motion betweening network. It's just network. It's a transform-based method. However, the thing is we can generate or synthesize a motion given its initial and final poses, and that's given. Or we can add more anchor poses so that it could interpolate those motions, those poses. And we can also give semantic meaning on that, semantic conditioning, so that we can add some more styles to those, synthesized motion. So it's good to see some. So this is called the unconditioned MIB. MIB stands for motion in between. You can see that we are only given this red and blue initial and final poses, and all the intermediate sequence of poses are generated from the transform model that we developed. So this has actually been presented last year by Ubisoft, the motion between itself. So we want to delve a little bit more into that. So this is a semantic condition motion between. You can see that we can condition on this aiming, dance, jump, and walk. Though it's not that perfect because this performance is wholly conditioned on the data set they provided. However, you can see that even though we're given the same initial and final poses, the synthesized motion is a little bit different based on the semantic meaning that we give, especially if she's dancing, you try to do some shuffle-like dancing. On jump, you try to do like a 1 foot jumping and so forth. And you can do a little bit more like dance condition, fight condition, jump, walk. So we try to make it as a conditioned or controllable motion synthesis. And since we have a whole pipeline of, if we have those motion capture data, we could easily transfer it to the real robot. So we can have a whole pipeline of generating motion from our semantic embedding or semantic meaning, and then transfer those generated motion to the robot side. And they'll be really great because we can actually basically generate robotic motion from some semantic meaning like angry, walk, or happy something. So that is like the goal of this project. We can also do pose condition. You can see that even though given same initial and final poses, you can see that we could freely set the intermediate pose, which I call the anchor pose, so that it could make some diverse motions out of it. So that's called the pose condition motion between. And the final work that I like to present is the last work that it is in business called the interactive robot bust. And the paper title was released, the interactive robot gaze. So this is what we built. So not the robot itself, the robot was there. We designed an algorithm and some firmware coding on top of it. That's my friend Matt again. You can see the robotic bust here. Even though there's no skin here, there was skin. However, because of this IP issues, we were not able to present skin on this video, but there was a cool skin, trust me. And only thing that we can do with this robot is actually moving eyeballs and some face movement, which cannot see because we don't have any skin. We can make some motion, we can make some sound. We can also move eyebrows and mouth and so forth, and a little bit of neck motion. So the thing that I was doing on this project was called the attention engine. And that is basically about so the scenario is like this. So this robot is in some public area where there are multiple people in front of you. And then this robot should determine which person that this robot should interact with. So that is called the attention engine, which computes the curiosity level of each person given sensory inputs such as RGBD images. So if you see on the robotic bus, there was a Mintai RGBD camera mounted on the chest. So it tracked the human body movement and a little bit of association with the face information. And then it kind of computes which person is willing to interact with human beings, this robot. So it depicts one based on some thresholding and rule-based method. And then it do some interactive motion based on predefined motion database, which we call the behavior library. And it goes on and on based on the final state machine. So this curiosity level is something that I designed based on the feedback of artists and other animators. And it was really cool, actually, because we tested on not only the engineers, but also non-engineers inside the house, in-house. And we were able to get some positive feedbacks out of it, even though the robot was only able to do some very limited action because it only has a robotic bust. However, they were really interested on the interactive side, especially when they feel the robot is acting accordingly to their motion, then they feel this robot is a little bit of alive and they feel some freaky moments and they feel entertained and a lot of mixed feelings. So that's really cool moments for me, and they kind of give me some confidence about human-robot interaction can be a thing in someday. So this is what I try to make. Okay, so instead of having some concluding remark, I usually end up with this slide, a robot in every home. So a lot of people work on a lot of manipulation side, a lot of people work on locomotion side, a lot of people work on planning side, algorithmic side, and so forth. And robotics is like a mixed field. However, if you think about robot in every home, then robots should exist with human beings, where generating a motion or the motion that is being conveyed by human beings is actually very important, and which is not that much of big field until now. A lot of people do it in these days. So I hope, at least for those who are listening to the seminar, I hope you guys should be more interested on that and try to do not only on some efficiency or energy efficiencies or speed and so forth, but also think about something like naturalness, expressiveness, which is really hard to evaluate, I know, but which can be helpful on someday making this a robot in every home possible. And for that, I'll finalize my talk with my colleagues and my sponsoring companies. And thank you all, and we'll be more than happy to get any questions. Thank you.
Thank you very much, Sungjoon, for the fantastic talk and the beautiful robot you work with and the motion strategy you presented. Do we have questions in the chat? So maybe I will have a first question. So in several of your work, you're mentioning the recent role of transformer networks. And I would be very curious to know, from your point of view, this self-attention mechanism for pose analysis estimation. What do you think remains to do on that matter, using this kind of model and this kind of network?
So let me make it more clear. So you're asking about like the self-attention module in
Yes.
transformer. Is it effective on this problem? Is that the question?
Yes, exactly. Exactly.
That I honestly don't know. The main reason, so basically what Ubisoft did on their motion in betweening, they use RNN model with teams. And basically that's autoregressive model, making the generation a little bit slow, as you know. If you use autoregressive transformer, then things are similar, but we use non-autoregressive transformer like BERT. So main advantage of using the transformer was the speed. And furthermore, because it's really faster to train with transformer because it can be parallelized, we were able to come up with a better, epochs and better training speed, better tuning time. So actually the performance of robust machine betweening of the transformer that we use is a lot better than the one that the Ubisoft presented on their paper using the LSTM. We actually replicate the LSTM model as well because they don't share the code, but based on their paper, we implemented LSTM transformer and we found the transformer to be more effective in terms of both accuracies and speed of training and inference.
Makes a lot of sense. As questions are coming, please do not hesitate. If any question, do not hesitate to type on the chat directly. Me actually have another question, which is more about natural motion with contact. Because at the moment, it's true that it seems that most of the motion are related to, of course, the posture, but I would be very curious to know your opinion, Sungjoon, on how to generate this kind of natural pose and natural motion when it comes to manipulating object, for example.
That's an excellent question, by the way. So you see a lot of faces of Matt, who was my office mate, and his expertise on handover. So he basically did the physical human robot interaction. So we shared this office. So we don't have a perfect answer to that, honestly. But the idea that we had is about the momentum. So there should be something that we should transfer from human beings to robot to make it like human-like. And there are multiple aspects of things that we can transfer to robots. And something that we focus on was the momentum. So we can basically, if you can somewhat compute the momentum that's being transferred between handover between human beings, if we can mimic that on the robot side, then they'll be pretty, cool idea. We don't have any chance about the evidence yet, but yes, that would be my answer to that.